Moving on to Module 3, we're going to get into functions and modeling. Today we're going to be dealing with graphing relationships, interpreting graphs, and modeling with functions. A lot of vocabulary, so please make sure you pause the video to write down all these definitions down, especially in the next 5 slides. So first, let's talk about a discrete graph. These terms that I'm about to show you within the next few slides are terms or vocabulary terms that you may or may not have already heard. So especially if you have not heard of these vocabulary terms before, make sure you write them down in your notebook. You could read what a discrete graph is, but a discrete graph is basically just going to look, and that should be distinct points, not distant points. Sorry about that typo there. That should be distinct points. Okay, so a discrete graph is just going to look, if we have a coordinate plane here, it's just going to be points that may or may not be related, okay? But they're not connected. That's the main thing. Whereas a continuous graph, you are going to have a connection. It could be a curve, it could be a straight line, it could look like a V, but the main thing is it's going to be connected by a line or by a curve. Next, a relation. A relation is just a set of ordered pairs. An ordered pair, remember, is just x comma y, where the first portion of an ordered pair represents where we're moving on the x-axis, and the second portion of an ordered pair represents where we're moving on the y-axis. A relation would just be a set of them, so more than one. 2, 3, 5, 7. Right there we have more than one, so that would be considered a relation. You could have 2 ordered pairs, 3 ordered pairs, or you could have an infinite amount of ordered pairs. As long as it's more than just one, it's a relation. Okay, while we're talking about relations, these words that I'm about to show you, you might have already heard of, but when we're talking about all the x values of a relation, we call that the domain. And when we're talking about all the y values of a relation, we call that the range. So let me write 3 or 4 points down. So the 3 ordered pairs that I just wrote down, the domain values would be 2, 3, and 5. Those are all the x values of those ordered pairs. That would be the x values of the relation, whereas the range would be 3, 7, and 9. Now we'll talk about function. A function is a relation, but it's a special relation in which each input has exactly one output. Each input, x, has exactly one output, y, and we'll talk more about that in a moment. So in a few slides, so you really know what a function is. But the important thing is that each x must be connected to only one y. That's the important thing. That's what makes a relation a function. Now, if we're given just a set of ordered pairs, the way we to figure out whether a relation is a function is by seeing if any of the x's repeat. Okay? If they do, the relation would not be a function. But if we're given a graph, there's another way of telling whether a relation is a function, and that's with the vertical line test. We're going to go through this quickly, but we're going to talk more about this in a few slides and during tomorrow's lesson. So basically, vertical line test, if you take a vertical line and you run it through the graph of a relation, if that vertical line touches the graph no more than once, it is a function. Okay, so what do I mean by that? Here I have a vertical line, right? And if I run this vertical line through the graph of this relation, you could see that at no point does my vertical line touch more than one part of this relation, of this graph. Therefore, that is a function. Same with this parabola here. At no point does my vertical line touch the parabola more than once. And same with these two bottom graphs, these two bottom relations. But if you look at these graphs that are correctly labeled not functions, if we run a vertical line through any of these 4 relations, any of these 4 graphs, you could see that, hey, right here, the vertical line is touching more than one point. It's touching 2 points. Same with this relation, same with this relation, same with this relation. It's always touching more than one, not always, but at one point it touches more than 1 point. Therefore, those are not functions. Let's move on to interpreting graphs. So here we're given a graph, and it represents this particular situation. But before we get to the situation, I want you to try and figure out whether this would be a continuous or a discrete graph. Hopefully you said it was continuous. Okay, this is the very definition of a continuous line. Everything's connected, and we don't have just distinct points, which that would make it would be discrete if we just have distinct points. Now, This particular situation represents a delivery van. The distance of the delivery van is from the warehouse varies throughout the day. The graph shows the distance from the warehouse for a day from 8 a.m. to 5 p.m. So if we look at a graph and we're analyzing this particular problem, that means right here, that means that we are at the warehouse and no time has elapsed. Okay, X represents time, Y represents distance, right? And if we look at this graph and we look at the first segment and we try to analyze what's happening in the first segment, it looks like, remember, Y means the Y-axis is the distance from the warehouse. So it looks like we're moving further from the warehouse and a certain amount of time is passing as well. Okay, now part A talks about segment 2. So segment 1 shows that the delivery van moved away from the warehouse. What does segment 2 show? So let me show segment 2 here in yellow. So if I put this here in yellow, okay, it looks like we're still moving away from the warehouse, right? We're still moving away from the warehouse. We're moving further on the y-axis, but we didn't cover as much ground in as much time. As you can see, the time that has elapsed, I should have used yellow, sorry, is greater than segment 1, okay? And the time is greater, but also the distance covered is not as much as segment 1. So think about what that might mean with this delivery van, okay? So this probably means that the van is traveling at a slower speed. It's not covering as much distance. Maybe it got off of the highway and is just on regular roads now. It has a lot more stop lights that it needs to deal with. It's not covering as much distance. So what does segment 2 show? It shows that the van is traveling at a slower speed than segment 1. All right, now based on let's go on to B. Based on the time frame, what change in the distance from the warehouse is represented by segment 6? So if you look at segment 6, I'll do that in green. So segment 6, it looks like we still have a certain amount of time that has passed by, all right? And we're still traveling, we're moving, but it looks like we're moving in the opposite direction. We're moving back towards the x-axis, we're moving back towards the warehouse, okay? So what does a segment 6 represent? It means it shows that the truck is beginning to return to the warehouse, okay? That's what segment 6 would show. Segment 6 would show that the truck is returning to the warehouse. Okay, so now which segments show intervals where the distance did not change? Okay, remember the y-axis is our distance, right? And if we look at this graph, in order for the distance not to change, it would mean that we'd need a horizontal line. We wouldn't be moving on the y-axis. Obviously, time would still keep ticking. We just wouldn't be moving. And if you look at this graph, the 2 segments where we have the 3 segments where we have that horizontal line would be 3, 5, and 7. Okay, so that would be 3, 5, and 7 for our segments where distance does not change. What are some possible explanations for these segments? I want you to think about that, see if you could answer it. I'm going to answer it in a few seconds. But this will probably mean that we're stopped for a certain amount of time, and this is longer than just a stoplight or anything like that, or a stop sign. So this probably means, this is a delivery van, right? This probably means that the delivery van is delivering packages during this time, is what I think these segments would represent. So explain how the slope of each segment of the graph is related to whether the delivery truck is not moving, is moving away from, or is moving toward the warehouse. So slope is a word that I hope you've already heard of before, but if you haven't, slope is just a measure of the steepness of a line, also the direction in which a line is moving. That's a good definition to write down, especially if you did not know what slope was before. So if we look at all these different line segments, it looks like when we have a positive slope, which positive slope means that we're moving up from left to right. When we have a positive slope, that shows that our delivery truck is moving away from the warehouse, okay? And when we have a zero slope is represented by this horizontal line. Anytime you have a horizontal line, we say that we have a zero slope. When we have a zero slope, that shows that the delivery truck isn't moving at all. And then you could guess it when we have you probably guessed it already. When we have a negative slope, that means the truck is moving away, I'm sorry, toward the warehouse, okay? And I want you to also, we'll talk about this more tomorrow, but I want you to also think about the steepness. What does the steepness of each line segment represent? We spoke about it briefly in the previous slide, but also think about that, have that in your mind for tomorrow's lesson when we discuss these type of problems even more. All right, and the last thing we're going to want to do is we're going to want to go ahead and represent relations and functions in 3 different types of models, using a table, using a graph, and using what we call a map, using mapping, okay? So here we're given a relation. Remember, a relation is just a set of ordered pairs, okay? And we do have a set of ordered pairs. We have 5, 10, 6, 20, 6, 23, and 7, 35, okay? Pause the video, go back to the definition of a function, and before we even start graphing all of these and putting these on a table, I want you to try to figure out whether this would be a function or not. I hope you realize this would not be a function just by looking at it, because our x's repeat. We have 2 6s, and that right there is a clear sign that this is not going to be a function. And we're going to also do this with the vertical line test in just a moment. So let's go ahead and represent this relation using a table. Now remember, an ordered pair is x comma y, right? So if we're representing this relation using a table, we would just put all the x values on the left column and all the y values on the y column. And this would be our table model. All right, now if we're showing this on a coordinate plane, so here we're given quadrant 1 of a coordinate plane. Remember, these are ordered pairs, so the first portion of the ordered pair represents where we move on the x-axis, and then the second portion represents where we move on the y-axis. So our first ordered pair is 5, 10. And to plot a point, you just put a point right on 5, 10. Okay, then next we have 6, 20. So you move 6 spaces on the x and 20 spaces on the y-axis. Then we have 6, 23, which is going to be right here, before 25. And then we have 7, 35, which is going to be all the way up here. All right. Now remember what we spoke about with vertical lines. So if we do our vertical line test here, even though hopefully you see that this is a discrete graph, right? It's just a set of points. But if we do the vertical line test and we run a vertical line through this graph, you can see that right here, our vertical line is touching more than just one point of this relation. It's actually touching 2 points on this relation. So therefore, that's another way of telling that this is not going to be a function. This relation is not a function. And last but not least, mapping. So mapping is very easy. The left portion of our map represents our domain, and the y portion represents our range. So when we're mapping, we only really need to put the domain and the range values just once. What do I mean by that? Well, if you notice in our ordered pairs, we had 5, 6, 6, and 7 for our domains, right? We would not have to put 5, 6, 6, and 7. We would just have to put 5, 6, and 7. And normally when we're constructing a map of a relation, we would put them in order of from least to greatest. So the smallest domain value would be 5. We'd put that first. Then we'd put 6, and we'd only put 6 once. And then we would put 7. And you might be asking, well, Mr. Ramos, how are we going to represent both ordered pairs that contain a domain value of 6? I'll show you in a minute. And then the range values are 10, 20, 23, and 35. So order them from least to greatest. None of them repeat, so we'd have to put all of them, 10, 20, 23, and 35. And when we're showing a relation through maps or using mapping, what you would do next is you would just connect them with a line that has an arrow. So what do I mean by that? Our first ordered pair was 5, 10, so we would just connect 5 with our range value of 10. Our second was 6, 20. We would connect 6 with 20. And here's why we didn't have to repeat the 6s, because we could also just draw a line from 6 to 23, okay? And that's how we represent that we had an ordered pair that had 6 twice as a domain value. And then 7 would be with 35. So these are the three ways to represent functions and relations. This is not a function, but these are the three ways of representing a relation. You could use a table, you could use a graph, and you could use mapping. Make sure you look over these. Make sure you watch the video again if you were a little confused. Have all these notes ready. I'm going to check them tomorrow, and we'll do more examples and more problems like these tomorrow. See you tomorrow.